Might as well record all of this. Okay, so calculate f of 7. Okay, remember that this notation is just a fancy way of saying our input, which in this case is our x, is going to be 7. So we are going to input x equals 7 into function f. So we take function f, and everywhere I see an x, we're going to put in a 7. So I get -3, absolute value 7 minus 2. My minus signs don't show up so good. Plus 5. Okay, absolute value works like parentheses. That means that 7 minus 2 is grouped together within the absolute value. So you need to do that first. So I now have -3 times the absolute value of 5 plus 5. And now I'm going to multiply. I'm going to multiply -3 times the absolute value of 5. The absolute value of a number is how far is it from 0 on a number line. So the absolute value of 5 is 5. If it's negative, then absolute value turns it into positive because it's a distance, so it's always going to be positive. But the absolute value of 5 is 5. So -3 times 5, we get -15. And then we have our plus 5. So the last thing we do is we add, and f of 7, whoops, will be -10. Okay, so you substitute in the 7 and then simplify it down until you have your output. So when you input a 7 into function f, our output is -10. Okay, part B says calculate g of -4. So again, this means we're going to take function g this time, and we're going to input x equals -4 into function g, which is up here. So I'm going to take function g, and every x is going to become a -4. And you notice that I always use parentheses when I input, especially negative numbers. Okay, parentheses. We do parentheses first. Here, the only thing to do to the 4 is make it negative. So in other words, there's not really a calculation in there. It just says make the 4 negative. Okay, it's negative. Now we do exponents. So this is actually the first calculation that we are going to do. We're going to take our -4 and we're going to square it. And -4 squared means -4 times -4, which is +16. Now we can do multiplication and division. There's no division, but there is multiplication. So that's -48. And then we take away 5 and we get -53. Okay. Common mistakes on this is first thinking that you multiply here and then square it. We do not do that. We always do exponents before multiplication. But that's a common thing, is that people will look at this and try to do the -3 times the -4, get 12, and then square the 12. And you'll notice that that would give you a 144 here, completely different value. So don't do that. And then the other thing is forgetting that when you square a negative, you actually do get a positive value. So -4 squared is +16. Okay. And then that takes us to this problem here, which is we have 2 points. -5, -3, and 3, 5. And we want to figure out the equation of the line that goes through those 2 points. Now, you'll notice that there's a graph grid. That means, yes, you could solve this on a graph. Solving things graphically is one of the ways that we learned how to solve. So there's nothing wrong with graphing it. However, I also want to remind you that we learned how to figure out the slope and the y-intercept without graphing. So there's my first point, and there's my second point. And what we need to do to figure out the equation of the line is y equals mx plus b. So we got to calculate and figure out what m is, and then we also have to figure out what b is. So from this table, I can figure out what m is by looking at the change in the x and the change in the y. So here's my x's. My x's increased by 8. You go from -5 to +3, that's an increase of 8. You go from -3 to 5, that is an increase of 8. Here's my delta y, here's my delta x. So remember that this value over here is called delta y, this value over here is called delta x. Slope is delta y divided by delta x. So for this problem, it's 8 divided by 8, or the slope is 1. We now have the slope. If you graphed it, you would put these 2 points on a graph and you would draw the slope triangle between them. And your triangle would have a rise of 8 and a run of 8, and you would tell me that the slope is 1. So yes, you could do this by graphing. Okay. Now we need to find B. We need to find the y-intercept. Okay. So B right here, I can use my slope that I just calculated, and I can use one of these points. Doesn't matter, I've got 2 points here. So I'll pick one. I'll pick the 3, 5, because that seems to be more people like to pick the positive values. Doesn't matter, but I'll pick that. So I'm going to go to y equals mx plus b, and I'm going to substitute in 1 for m, 3 for x, 5 for y. So there's my y equals, my m is 1, my x is 3 plus b. So I substitute that all in, and now I can figure out what b is. So here I have 5 equals 1 times 3 is 3 plus b. Subtract 3 and b is 2. So there's my slope right here. And there's my y-intercept right there. So my equation is y equals 1x plus 2. 1x is the same as x, so the 1 is completely optional. You don't have to write the 1. So my equation is y equals x plus 2. Okay. So there's my equation. Whoops, bring my pen back. There it is. And then the last question here is the point -2, 4 on this line? So one way to do that, graph the line if you didn't already, and literally look and see whether that point is on the line. Another way to do it is to take the point -2, 4. Is this on the line or not? I'm going to put this in for x and that in for y into my equation, and we're going to see whether it works. If -2, 4 is on the line, it needs to work in this equation and give you a true statement. So the y is 4, so I'm going to put a 4 right there. And my x is -2 plus 2. So I add -2 plus 2 is 0. 4 equals 0 is not true. 4 is not equal to 0. So that means it is not on the line. The only way that it can be on the line is if these two numbers come out to be equal to each other. So therefore, you don't want to write the word therefore, which is a long word. 3 little dots mathematically means therefore. So therefore, -2, 4 is not on the line. Okay, so -2, 4 is not on the line. Again, if you prefer solving graphically, graph the line. Find -2, 4 on your graph, and you will see that no, it's not anywhere near the line. Okay, so -2, 0 is what would be on the line, not -2, 4. Okay, so that is our warm up. And the only other thing we're going to do is take some notes. So notes are in Schoology. I'm waiting for them to show up here. Oh, my internet is not connected. Let's see what's up with that. Give me a second here. Searching for Wi-Fi networks. Okay, there it is. I don't know why it dropped for a second. But chapter 4, we're going to be looking at sequences. And what I decided to do in this chapter, instead of having you guys do all the chapter 4 notes and then just turn them all in at the end of the chapter, I'm just going to have you guys turn them in at the end of each day after we take them, because I think that'll be easier for you and you don't have to, keep track of all of them. So we'll just take notes. At the end, you copy them down while I'm doing them. On Cami, for example, just hit turn it in at the end of the period, and then you'll just turn in your notes each day. So I'm just thinking that will be easier for us. So we're going to at least try that this chapter. So if you go on Schoology, you will see that there is a chapter 4 notes. It says pages 1, 2, and 3. So that's what we're doing today. We're going to do the first 3 pages of the chapter 4 notes. Okay, so they're on Schoology. If you can't access Schoology or don't want to use Cami, you can write all of this down on a piece of paper, scan it in, and then just turn it in later today. Okay, so I am going to ask you to just do that each day. It'll be easier, I think. So I'm hoping that it'll be easier. Okay, a sequence. A sequence is a pattern of values. That's pretty much what a sequence is. So here is a sequence. This is called sequence A. So a sequence might have a name based, given a letter name. It might not. You might just be given, here's the sequence, 1, 3, 5, 7, etc. But here is sequence A. So what you need to be able to do when you see a sequence is figure out what the pattern is. How is this sequence being generated? Like right here, it says, what are the next 2 terms in the sequence? Okay, the terms are the values in the sequence. For example, in this sequence A, I could tell you that the first term is 1. That's a way that I can say first term, A sub 1 is 1. First term is 1. My second term is 3. My third term is 5, etc. So that's a notation. When you see A sub 1, that just means the first term. A sub 2 means second term. A sub 3 means third term, etc. Now it says, what are the next 2 terms? So do you guys see the pattern that's going on here? Now, how is this sequence being generated? Sure, somebody can see it. Yeah, Star? Yeah, so what are we adding each time? 2. Yep. Nope. Notice here, we go up 2. And then we go up 2. Up 2. So that means my next term should be 9, and then it should be 11, etc. So there are my next 2 terms. 1, 3, 5, 7. The next term would be 9, and then 11. Another way that I could denote the terms in a sequence, I can do this notation, but I can also use function notation. I could say A of 1 is 1, A of 2 is 3, A of 3 is 5. That's just a completely different way to say the exact same thing. So just know that you might see the notation either way. This is function notation. The number in the parentheses is the term number, and then this number over here is the value of the term. So term number 2 has a value of 3 right here. Term number 3 has a value of 5. So this is the actual term number, and this is what is the value of that term. And then it says over here to write down how is the sequence generated. So we can say add 2 to the previous term. So that's what we did. We added 2, added 2, added 2, added 2, added 2, and then that's how we were able to get the next 2 terms in our sequence. Okay, sequence B, 2, 4, 8, 16, 32. This one is different. Do we see a pattern? And notation, I could say B sub 1 is 2, could say B sub 5 is 32. 1, 2, 3, 4, 5. Those are just some notation. I could say B of 3, third term, is 8. That's just notation that you might see. But the question is, what are the next two terms? What's going to come after 32? No one in the chat has said so either. What comes after 32? Yep. 64, that is correct. And then what? 128. There we go. That was a little harder, bigger number. But what's going on here? It's doubling. So right here, we're multiplying by 2, multiplying by 2, multiplying by 2, etc. Okay, so this sequence is generated by multiply the previous term by 2. Okay, so that's how we're generating that one. We're multiplying the previous term by 2. Okay, next one's a little harder. So 2, 3, 6, 11, 18. Okay, does anyone see it? Okay, looking in the chat. Looking at the class. Okay. As a hint, take a look at what's being added each time. Okay, so some thoughts here are add half of the previous or add the past numbers. Those are not quite correct. So let's take a look at some adding here. To go from 2 to 3, what do you add? Come on, guys. What do you add 2 to get 3? Yeah, 1. There we go. From 3 to 6. 3. And then we add 5. And then we add 7. So what should we add next? 9. So if we have 18, we'll add 9, which will take us to 27. And then we'll add 11, which would take us to 38. Okay, so this sequence is being generated by add the consecutive odd numbers. Like +1, +3, +5, etc. Consecutive means in a row. 1, 3, 5, 7. Those are the consecutive. They're not like 1 and then 9 and then 11. It's in a row. So first add 1, add 3, add 5, etc. Okay, next one. Sequence T. This is back to being a little easier. What's going on here? Yeah, we're subtracting 3 each time. So right here, subtract 3, subtract 3, subtract 3. So if we keep going, we'll get -2 and then -5. So we are subtract 3 from the previous term. Okay. The next sequence on the page is the exact same one, so we're not going to do it twice. So we are done with page 1. Okay, so page 1, we were just looking at different sequences, trying to figure out what the pattern was. And then we talked a little bit about the notation, okay? So when you see a little number in the right-hand corner, lower right-hand corner, that's the term number, okay? Second page. There are two types of sequences that you need to be able to distinguish. The first one is called an arithmetic sequence. Yes, this is the exact same spelling as the word arithmetic, but arithmetic is a noun. And when we put it in front of a noun, it's now an adjective. And then our screwy language decides to pronounce it differently. So now it's arithmetic, even though it is the same spelling as arithmetic. So an arithmetic sequence is a sequence that has an addition or subtraction generator called the common difference. Now, common means that it does not change. So when we say that it's addition or subtraction, it needs to be the same value. So this common difference is a constant value. So that means we either add or subtract the same value every single time, and we get an arithmetic sequence. The common difference, we're going to call it D. To find the common difference, you take a term. For example, let's take the second term and subtract the one before it, the first term. So the common difference would be a sub 2 minus a sub 1. But it could also be a sub 3 minus a sub 2. Could be a sub 10 minus a sub 9. So in fact, it really is just take any term number you want. So n for any term number you want, and then subtract the previous one. So if you want to take the 100th term, subtract the 99th. That's an n minus 1 right there. So you can subtract any two terms that are next to each other in an arithmetic sequence, and you can get the common difference. So if we go back to page 1, our first sequence, A, you guys agree that that one's arithmetic? Are we adding the same number every single time? Yeah, this is arithmetic. So this sequence right here is arithmetic. And if I asked you to figure out what D is, take any two numbers in the sequence that are next to each other. For example, I'll take those two, 1 and 3. So my common difference is I take 3 and I subtract the 1 right before it. 3 minus 1, my common difference is 2. But we already knew that. We knew that we were adding 2. Okay, but that's all it is what number are you adding each time? And that's how you figure it out. Just take two numbers in the sequence and subtract them. That's why we call it a common difference. A difference means subtracting. So you find a common difference by subtracting any two numbers next to each other in a sequence. Okay, sequence B. You guys agree this is not arithmetic? We're not adding the same number here. Here we would add 2, then we would add 4. This is not arithmetic. Neither is this one. We're adding, but it's not the same number every time. We added 1, then we added 3, then we added 5, then we added 7. This is not arithmetic. But what about this one? Is this arithmetic? We'll go back to the definition here. It says an arithmetic has an addition or subtraction generator. So what do you guys think about sequence T? Is that arithmetic? Yeah. As long as you're subtracting the same number every time, it's arithmetic. So this one is arithmetic. And our common difference, take two numbers. I'll do the 4 and the 7. Common difference. You take a number in your sequence, 4, and then you subtract the number that's before it. Make sure you're always subtracting the number from that's in front. So it's 4 minus 7. It is not 7 minus 4. It is 4 minus 7. This makes our common difference -3. So an arithmetic sequence that is subtracting is the same as saying the common difference is a negative number. So in other words, yeah, I could say this is subtracting 3, but I could also say it's adding -3. So it's the same thing. Saying you're adding -3 is the same as saying you're subtracting 3. So we can just get rid of the whole idea of subtraction and just stick with addition. This is an arithmetic sequence because we're adding -3 every time. The common difference is -3. Okay, our second type of sequence is called a geometric sequence. And a geometric sequence has a multiplication or division, because they kind of are the same thing, generator that is called a common ratio or a multiplier. The most common thing to call it is a common ratio. So we usually use R for the common ratio. And common ratio means divide. So like take the second term and divide by the first term, and you will get a common ratio. A ratio literally means what you get when you divide. This is a ratio. When you divide two numbers, it's a ratio. So that's why it's called a common ratio, because you calculate it by dividing two numbers. But it can be any two numbers in your sequence. So pick a number. Any term you want, but you divide it by the number that's in front of it. And my minuses come out so weird sometimes. That's n-1. Okay, so take the 10th term in your sequence and divide it by the 9th term. Take the 1000th term and divide it by the 999th term. It does not matter. Pick any two numbers in your sequence that you want, and you can find the common difference. On the first page, sequence B was the geometric one. So this one is geometric. Take any two numbers right here. I'll take the 8 and the 16. We're going to find the common ratio. We're going to start with the 16 and divide by the number in front of it. Make sure you divide it in the correct order. So we take 16 and divide it by the 8. Or you take the 8 and divide it by the 4, but you're always dividing by the number in front. You're dividing by the previous term. And 16 divided by 8 is 2. And you'll notice, hey, we were multiplying by 2. Okay, so that's what we expected. Geometric, we were multiplying by the same number, in this case, 2 every time. So back to page 2. Now that we know the difference between arithmetic and geometric, by the way, this other one that we did here, that one doesn't have any special name. So we could call it other, but it has no special name. So every sequence that you see, we will be categorizing it as arithmetic or geometric. And if it's neither, you can write neither or other or not one of the ones we learned, because those are the only ones that we're going to learn is arithmetic and geometric. So right here we have some sequences. It says for each sequence below, determine if it is arithmetic or geometric and describe the generator. If it is arithmetic, the generator is going to be a common difference. If it is geometric, the generator is going to be a common ratio. So if you decide that it's arithmetic, you got to give me a common difference. If you decide it's geometric, you got to give me a common ratio. Okay, ratio means you're going to divide numbers to get it. Difference means you're going to subtract numbers to get it. So here's our first one. 5, 10, 20, 40. What kind of sequence is this? So arithmetic or geometric? Yep. What are we adding? It's geometric. Good. What are we multiplying by? Well, let's find out. Common ratio. We take two numbers. Pick two numbers and divide them. Yeah, 2. So common ratio, just take two numbers from your sequence, take one number and then divide by the number in front of it. And you can see that our common ratio is 2. So this is a geometric sequence with a common ratio of 2. That means you get the next term by multiplying by 2. So 5 times 2 is 10, times 2 is 20, times 2 is 40, etc. Okay, there's our next one. And all of these are going to be one or the other, okay? So is it arithmetic or is it geometric? And if you're not sure, just pick a couple of numbers. See whether you're adding the same number every time or whether you're multiplying by the same number every time. So what do you guys think about this one? Okay, Star? Arithmetic, okay? So arithmetic. So arithmetic means that if I take two numbers, any two numbers in my sequence and subtract them, I should always get the same thing. So D for common difference. If I take -7 and subtract the number in front of it, and notice that I am subtracting a negative, so I'm going to do -7 minus -2, which gives me -5. So let's make sure that works. -2. You add -5, you get -7. Add -5, you get -12. Add -5, you get -17. So this is definitely arithmetic with the difference of -5. Okay. This is our last one here. I know fractions can freak people out. But if we think about the whole idea of arithmetic versus geometric, can you ever add numbers and end up with a fraction unless you're adding fractions? So since there's no fractions here and all of a sudden there's fractions, what does that kind of mean it's got to have to be? Yeah, geometric. Now let's figure out our common ratio. Take two numbers that you would like to divide. I'm imagining you guys would prefer to divide those two, right? Because they're not fractions. It is divided by 3. However, a common ratio we find by taking a number in the sequence and dividing by the number in front of it. So we take 4, we divide by 12. This is a fraction that reduces to 1/3. So you're absolutely right. This is a sequence that is generated by dividing by 3, but that is the same thing as multiplying by 1/3. Just like when we say that the common difference is -5, we're adding -5, but some people will see this as subtracting 5. It's the same thing. Multiplying by 1/3 is mathematically the exact same thing as dividing by 3. So if you said, hey, we're dividing by 3, you're right, we are. 12 divided by 3 is 4, divided by 3 is 4/3, but that is true. But we could also say we're multiplying by 1/3. And since we want to give the common ratio, 1/3 is the better answer. So to say that, how do you get from here to here? You multiply by 1/3. How do you get from 4 to 4/3? You multiply by 1/3. How do you get from 4/3 to 4/9? You multiply by 1/3. And then you're going to end up with a fraction. All the rest of the terms are fractions. And how is the fraction going to change? Well, the top number will get multiplied by 1, and the bottom number will get multiplied by 3. So my next term, if I multiply by 1/3, top gets multiplied by 1, bottom gets multiplied by 3. So I could keep going. My next number, top gets multiplied by 1, bottom gets multiplied by 3. So that would be what, 381. Okay. But yeah, we're dividing by 3. But we're going to call it a common ratio of 1/3, which is multiplying by 1/3. Okay, the last thing I want to look at on page 3 is the graph of a sequence, which is not that difficult. Okay, when we graph a sequence on the horizontal, we are going to put the term number. Okay, term, first term, second term, third term, fourth term must be a whole number starting at 1, and there's no negatives, and there are not going to be any decimals or values in between. You have term number 1, you have term number 2. There's nothing in between. On the vertical axis, we're going to put the term value. So if we take a look at this sequence right here, that's my first term. There's a dot right there. Term number 1 has a value of 0. So there's my first term. Term number 2 has a value of 3. Term number 3 has a value of 6. Term number 4 has a value of 9. And I know it says 6 terms of the sequence. The graph only gave us the first 4, but I think we can figure out what kind of sequence this is. So what is this? Plus 3. So that makes it arithmetic, right? So this is arithmetic with a common difference of 3. So yeah, we can find the next first 6 terms. There's 1, 2, 3, 4, and then there's 5, and then there's 6. So there's the first 6 terms of our sequence. Here, F sub 10. That means what's the 10th term of the sequence? So here's our first 6 terms. That's what the first question asked. But we could keep going. So 1, 2, 3, 4, 5, 6. My 7th term would be 18. And then my next term would be 21. And then 24. And then 27. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My 10th term, because remember that's what that is asking, is 27. Okay. F of 15. That means what's the 15th term? So let's keep going. There's my 11th term, my 12th term, my 13th term, my 14th term, and my 15th term. So my 15th term is 42. It was not that hard to generate this sequence and figure out term number 10 and term number 15. So it was not that difficult to do that. However, we are not today, but later on, we're going to learn a more efficient way to do this, because if I asked you to find term number 68, you probably do not want to continue just adding 3 and getting all the way to the 68th term. So there will be a more efficient way for us to do that. But for now, this was easy enough because it was only the 10th and the 15th. Okay? So describe, how do you go from one term to the next? So what are we doing here? We add 3 to the previous term. And remember, that made it arithmetic. Arithmetic with a common difference of 3. That's the same thing as saying this is arithmetic with a common difference of 3. Now, describe how the graph changes. Take a look at the graph. Now, first off, when you graph a sequence, we will only be graphing dots because there are no values in between. This is the first term, this is the second term, and if I were to connect them like this, then I'd be saying, well, there's a bunch of values in between. There aren't. Our sequence is literally that number, then it jumps to that one, then it jumps to that one, then it jumps to that one, etc. So a sequence is only dots. We call this a discrete graph. It's not continuous. It doesn't continuously go. It jumps from here to here to here to here. Now, even though it does that, I can draw a line just to visualize what's going on. And if I connect them you can see that, yeah, this is actually linear. So even though the point's not connected, you can see that it is a linear graph, and every point goes up 3 over 1. So what does this graph look like? Well, it's a linear pattern with a rate of change. Remember, rate of change is also called slope of 3. So the graph always has a change of 3. No matter where I go, from here to here, it's 3. From here to here, it's 3. So between any 2 points, it's always going to have that same rate of change between them. If you count the squares, it's going to be 3. Okay? Now, our last one here, I'm going to give you a sequence. So we got 1, 4, 16, 64. So part A, describe, how do you go from one term to the next? Multiply by 4. Okay, so we multiply the previous term by 4. So I've got 4 terms up here. So if I were to keep going, by the way, this makes it geometric. I would basically use a calculator because these numbers are going to get really big really fast. So here is my 4th term. My 5th term is 256. My 6th term is 1024. There's my 7th term, and there's my 8th term. So it asked for what's the 8th term. So my 8th term is 16,384. Okay, and please, with geometric, when they get big, fast like that, use a calculator. This is asking for the 10th term. So if there's my 8th term, I multiply by 4 again. There's my 9th term, and there's my 10th term. So lots of growth very quickly. So that's 262,144. Part D says, let's graph this. So again, remember that on the horizontal, it's the term number. And then on the vertical is the term value. So right here, we're going to graph 1, 1. Term 1, value 1. And you'll have to estimate where it goes. Because if you look here, I've got term 1. There's 20, there's 10, there's 5. So it's going to be like really close to the bottom there. Okay, so there's 1. Term 1 is 1. Term 2 is 4. So term 2, there's 20, there's 10, there's 5. So close to 5 right there, a little bit higher. Term 3 is 16. There's 10, there's 20. So 16 is about halfway between 10 and 20, a little bit more than halfway, but estimating. That term 4 is 64. So 60, 70, so 64 is about right there. And term 5 is 256. If you take that and multiply by 4, you get 256, which is just off the graph here. So I'll put it up there. Okay, so if we take a look at our dots here, are these growing in a linear pattern? No, you guys see that it's curved? Okay. Does anybody know the special name of this kind of curve? It's actually what our next chapter after sequences is going to be all about. This is called an exponential curve. And all you need to know for now is that geometric sequences, the graph is an exponential curve. So if you've ever heard of someone saying, oh, it's growing exponentially, for example, viruses grow exponentially, and all of the talk that we've had in the last 6 months, about flattening the curve and all of this stuff, all based off of exponential curves. So that is an example of something that grows like that. But take a look at what happens between our 2 points. The growth here, the rate of change is very small, gets a little bigger, then it gets way bigger, and then it's huge. So the rate of change increases very quickly. It doesn't stay the same. With linear, it always has the same rate of change. But here, the distance between the 2 points, the rate of change is increasing. So the rate of change increases very quickly. And we don't even really call it slope because it's changing. It's not the same. We only call it slope when it's constant, when it doesn't change. Okay? But this one was geometric. It had a common ratio of 4. So just a reminder, that's what that sequence was. That was a geometric sequence with a common ratio of 4. Okay, so let's see where we're at here. Good, just in time. So your Delta Math tonight is going to have you look at sequences, and then you're going to make a choice with a little drop down. Is it arithmetic? Is it geometric? And then with the drop down, you're going to also say, does it have a common difference? Does it have a common ratio? If it's arithmetic, it's common difference. If it's geometric, it's common ratio. So you just do the drop down on that, and then you type in the value. So like, for example, if you saw this on Delta Math 14664, you would say geometric, common ratio, and then you would type in a 4. And that's all the Delta Math is going to ask you to do tonight. So it's really just distinguishing between the 2 types of sequences. So determining whether it's arithmetic or geometric, it'll be one or the other, and then saying what the common difference is or the common ratio. Arithmetic has a common difference, like up here. And geometric has a common ratio. Okay, so we are done. Those of you guys that are online can go ahead and log off if you want. I'm going to stop the recording here. And then those of you guys that